Continuing with wanting to be able to take the Laplace transform of complicated things, we'd like to be able to take the transform of an integral. It's going to take us a little bit of work to get there, but that's our goal today. In order to be able to take the transform of an integral, we need to talk about something called a convolution. So if we have functions f and g that are piecewise continuous on the interval 0 to infinity, then the convolution of f and g that we denote with the symbol that's an asterisk between the two is the function defined by the integral from 0 to t of f of tau, g of t minus tau d tau. So let's just first take a look at what the convolution of e to the t and sine of t is. So the first thing, in order to use the definition very nicely, we need to identify an f and a g function. So we'll use f of t is going to be e to the t, and g of t is going to be sine of t. So now this gives us that f of tau is going to equal e to the tau, and g of t minus tau is going to equal sine of t minus tau. So now we're going to be taking the integral of e. So now, by the definition, we're going to be taking the integral from 0 to t of e to the tau sine of t minus tau d tau. Now we'll need to use integration by parts here because we have two functions involving the tau, and when we do that, we end up finding that our integral is 1/2 times e to the tau sine of t minus tau plus e to the tau cosine of t minus tau. And all of this is evaluated from 0 to t. So we'll be plugging in t for tau and then 0 for tau. And so when we plug in t for tau, we're going to get 1/2 times e to the t sine of t minus t plus e to the t t minus t plus e to the t cosine of t minus t. And then we need to plug in 0 for tau and be subtracting that, so we'll do minus e to the 0 sine of t minus 0. And then minus again, because we're still subtracting it, e to the 0 cosine of t minus 0. And simplifying this, our sine of t minus t is 0. So that first term goes away. Cosine of t minus t is, cosine of 0 is 1. So that becomes just e to the t. E to the 0 is obviously 1. And we've got sine of t and cosine of t. We have some extra negatives floating around. So this ends up being 1/2 e to the t that remains with our cosine minus sine of t and minus cosine of t. And that's the convolution of e to the t and sine of t. At this point, you might still be feeling like you have no clue where this is going and why we just did that, and that's really okay. So stick with me for a little bit. Hopefully it'll all come around to make sense why we're doing what we're doing in just a little bit. So we have something called the convolution theorem. So if we have f of t and g of t, they're piecewise continuous on 0 to infinity. That may be looking familiar. About our Laplace transform, yeah? And they're of exponential order. Then the Laplace transform of the convolution is going to equal the Laplace transform of f times the Laplace transform of g. So let's take a look at taking the Laplace transform of that convolution that we just found. So the Laplace transform of our convolution of e to the t and sine of t. Well, since we recognize it as the convolution, then we can rewrite it as the convolution. And then we can use our theorem that we have. So this is really just the Laplace transform of e to the t, because that was my f, times the Laplace transform of my g. So this is sine of t. It's my g function that I had. All I have to do is know what the Laplace transform of e to the t and sine of t, and I know both of those already. So there's no extra work here. So the Laplace transform of e to the t is just 1 over s minus 1. Laplace transform of sine of t is 1 over s squared plus 1. And so I'm multiplying those together, and I'll be multiplying across, so I'll get 1 in my numerator, and I'll get s minus 1 times s squared plus 1 as my denominator. And that's all there is to it. I now can take the Laplace transform of that convolution super easily. What might be even more useful is when you can recognize something as the product of two Laplace transforms and you need to take the inverse Laplace transform. So the inverse of that convolution theorem is saying, hey, you know what? When you notice that two things are Laplace transforms of functions that you know, and it's a product of the two, then the inverse transform, it's just the convolution. So let's take a look at an example of that. If I want to take the inverse Laplace transform of 1 over the quantity s squared plus k squared squared, I could say, you know what? I know that that is actually the inverse Laplace transform of 1 over s squared plus k squared times 1 over s squared plus k squared. And I could look at it and say, well, 1 over s squared plus k squared, does that look familiar as something I know that it's the Laplace transform for? Again, kind of. S squared plus k squared, I recognize that, and not having an s in the numerator was okay, but it had to have a k in the numerator if it didn't have an s. So what I'm really doing is taking the inverse Laplace transform of two identical functions. So that means that capital F of s equals capital G of s, and they both equal 1 over s squared plus k squared. And I look at that and I go, you know, I didn't have anything that didn't have an s or a k in the numerator. But it was okay that if it didn't have the k, because I could make up for that by strategically multiplying by 1. So what this really tells me is that g of t and f of t, they're the same, and they're going to equal 1 over k times the inverse Laplace transform of k over s squared plus k squared. So that's that strategic multiplying by 1 happening. And now I recognize the thing inside as being sine of kt. So this is going to equal 1 over k sine of kt. So now I know kind of how I can make use of these convolutions to help out with taking Laplace transforms back and forth with some integrals.